当师大。And Tim got his PhD from National Central University, and then later he became the postdoctoral fellow at the Hong Kong University, and later he got the JSPS postdoctoral fellowship and worked at the Kyoto University. And Tim is an expert on the high energy astrophysics. And today he will talk about exploring physics in extreme conditions. So multi-wavelength multi-messenger observation on contact object. So let's welcome Chimpi's talk.
Thank you for introduction. And do I need to use the microphone? Can you hear me from the end of the? Okay, good. So I will talk about contact objects and exploring the physics in the extreme condition. Because contact objects are including neutrons and black holes, they are natural laboratories to test physics in extreme condition. How extreme? For example, extreme high density neutron star, right? Extreme high magnetic field. We know that neutrons have very high magnetic field, especially magnetars. And extreme high gravity, high accretion rates, for example, ultraluminous. So they are natural laboratories, and we cannot reproduce those physical processes in our laboratory on the Earth. And today I will introduce isolated neutron star, accretion physics, accretion neutron star, black holes, ultraluminous, and my ongoing project about gravitational wave astrophysics beyond coalescence. And I'm developing the advanced time-sequence analysis method. And I am recently joining the pulsar project. They are aimed for the gravitational wave radiation. So let's start with pulsar. The simplest picture of a pulsar is a magnetic dipole, rotating magnetic dipole. And when the magnetic dipole gradually slows down, the energy released from the open field line and produce non-thermal synchrotron radiation. And the rotation energy loss, the magnetic field, and the age, characteristic age of a pulsar can be derived from the period and period derivative. The time, the slow down rate of the pulsar. And let's show you an example. The most famous example of pulsar, the Crab. Crab is a pulsar born in roughly 1,000 years before, and it shows pulsation in radio, optical, X-ray, and gamma ray band. So it is a multi-wavelength source. And one of the most interesting phenomena in Crab is a giant radio pulse. That is a sporadic radio pulse that are 2 or 3 orders of magnitude higher than normal radio pulses. But the mechanism is still unclear because we still have no detection in X-ray, although it provides some constraint. But we have optical observation, but in X-ray we have no GRP emission before. But they are candidates. Now we have a quotation mark because they are unlikely candidate, maybe, of the repeating fast radio burst. So you see that we are all astronomers, right? Astronomers usually use an unknown thing to explain another unknown thing. Right? We know GRP, but we don't know the mechanism. But we believe that they could be one of the candidates for FRB. This is an optical enhancement in GRP-associated cycles. So one of my collaborating project is to search for the X-ray enhancement of GRPs. And we use the NICER, which is an X-ray detector on the ASS, and use 2 radio telescopes to perform simultaneous observation. And you can see the host profile here. And after accumulating roughly 10 seconds of observation, we can get very good shape, pulsation shape. But in order to detect the enhancement, tiny enhancement, we collect 122 kiloseconds of observation, and roughly more than 24,000 giant radio pulses, and we detect, indeed detect X-ray enhancement for the GRT associated cycles. And of course, we can provide some constraint on the model, but still, there are many models can explain our results. So, still a long way to get to access the truth. We still don't know. And this is a graph I show you here. And this is the most famous PP dot diagram for pulsar. It is roughly the same as the actual diagram of star. It's very important in pulsar physics. And previous here, we believe that young pulsars are born in this region and evolve through this direction. But you can see that there are several groups of outliers. For example, here, they have extremely high magnetic field, and here, they have extremely short period, and they cannot be explained by the regular evolution track of pulsars. And we believe that magnetars are neutron stars, and they have some very extreme, very interesting phenomenon. For example, they have short X-ray or gamma ray bursts. They have long-term outbursts. And they have extremely high surface temperature, high X-ray luminosity, even exceeding the spin-down luminosity I showed you before. So we believe that, astronomers believe that they are powered by the decay of an extremely strong magnetic field. And those phenomena are related to the extremely high magnetic field. But you can, if you see here, there are several low magnetic field magnetars. And here, there are two high magnetic field radio pulsars. Their X-ray luminosity is lower than the spin-down luminosity, similar to those regular pulsars. But they show magnetar-like activities. So we believe that those so-called high magnetic field pulsars are missing link between magnetars and regular pulsars. And we now believe that they may form from the same group, and high magnetars are just the high magnetic field tail of pulsars. So the formation process may be the same. Okay, but actually, if you find something to fill in some gap, you effectively create two more gaps in between, right? So we always need to find more things to fill in gap. Many missing links to link them, these two groups together. And recently, this March, we find a new magnetar. The location on PV dot diagram is here, very close to magnetar group, but it has the shortest pulsation period. And the burst activity and outburst activity are very similar to those of magnetars. But the most interesting thing is that these both have radio emission. We detect the radio position. And if we plot the spin-down luminosity versus the X-ray luminosity, you can see here, this line is X-ray luminosity equal to spin-down luminosity. And regular magnetars are here. Regular pulsars are here. Several high magnetic field pulsars are here, and these two are high magnetic field pulsars with magnetar-like behaviors. And here are some radio magnetars that they have intermittent radio emission. And switch JT80 is here, right between these two groups. So in this diagram, the outburst peak luminosity still lower than its spin down luminosity. So in this diagram, this source is more close to high magnetic field pulsars. But in previous PV dot diagram, it behaves very like magnetars. So we find another missing link, fill in the gap. And magnetar is very important not only in neutron star physics, but also in phasor radio burst. As I said before, the GRP is one candidate for phasor radio burst. But actually their luminosity is still much lower than regular FRBs. And recently, roughly in April, there is a galactic phasor radio burst, and the location is coincide with an magnetar. And the land magnetar also very active when we observe the FRB. So this is a phasor radio burst, and this is the location, and the phasor radio burst is here, very close to regular FRBs. And unfortunately, we NICER do not observe the X-ray burst coincide with radio burst. But actually SMT observed that burst. And you can see that they perform a very good analysis in their spectrum. But roughly a few hours before this burst, NICER carried out an observation on this source. And this source has a burst storm, roughly 200 bursts in a few hours. And we carry out a characteristic to study the statistical property of their spectral photon index and the cutoff energy. We find that those so-called regular bursts and FRB associated bursts are quite different in spectrum. Although they have very, very similar timing behavior, but their spectral behavior are quite different. So magnetars could have two different X-ray bursts. One is maybe no association with phasor radio burst, and another kind is possibly phasor radio burst associated. So this solves one, at least we know part of phasor radio bursts are from magnetars.
Now, Qingping, how do you produce what the emission mechanism from the phasor radio bursts from magnetar? How do you generate such gigantic radio bursts?
It should have something, a lot of electrons or something on the near magnetic pole, and it sporadically ejected from the system or something, just like a GRP. It's very similar to GRP, but the magnetic field of magnetar is much higher. So I believe it is possible explanation.
So it's from the synchrotron radiation?
Synchrotron, yes, because we use power law. Yeah, synchrotron or inverse conjunct. Yeah. And very, very recently, there is another magnetar, so was discovered in roughly 1 month before. And this source also very active. During the flux decay, it has a lot of bursts. And we calculate the spin phase of those bursts, and we find that it is likely coincide with pulse profile, the pulsation. So those so-called regular X-ray bursts may come from the surface, not from the magnetic pole. And the those FRB bursts may come from the magnetic pole. So they could have different origin. But we need more data, so we still collecting data to make the statistics more significant. This is a very, very preliminary result. Okay. So there's a very simple story about magnetons and high magnetic pulsars. And those are very recent progress. And now I will focus on another group here, millisecond pulsar. So they cannot evolve from here. We don't believe that. And those millisecond pulsars were discovered in the 1980s, I believe. And they are isolated radio source. But the model, theoretical people predict that they should evolve from binary system. And indeed, complex objects, including black hole and neutron stars, can be observed in binary system. And they are very, very powerful sources, and the major emission from those kind of system are X-rays. So they are named as X-ray binaries. And slowly, the mass of complex object, the mass of companion star, they can be divided into low mass X-ray binary and high mass X-ray binary systems. And they could have different accretion mechanism. Can be divided into low-slope overflow system, wind-fed system, or for high mass X-ray binary, there's a special type of X-ray binary called AE X-ray binaries. They are formed in equatorial outflow of the B star. And how does those neutron stars in this system, how do they spin up? This is because if they have an accretion disk, and as long as the magnetic field is low enough, or mass accretion rate is high enough, then the disk can penetrate the so-called rotating radius. This means that the rotation speed here is equal to the spin of a neutron star. Then in this situation, the accreting material can be channeled through the magnetic field line and accreting onto a neutron star, and bring angular momentum to a neutron star and spin it up to millisecond level if the magnetic field is low enough. So the evolutionary track is like here. The poles are born here and fall through this way and recycled through this way, and to become a millisecond pulsar. And this was just a model in 1990s. And in 1998, astronomers find the first millisecond pulsar in X-ray binary. So it provides a very strong evidence that those millisecond pulsars could be formed in X-ray binary system. And as I say, find something fill in the gap, you will always generate two more gaps. So, and there are we astronomers try very hard to find out some evidence to strengthen this theory. And this is an example that we find a lot of systems, not a lot, only 2 or 3 or a few. They are so-called black widow or redback systems. We indeed see the evaporation of their companion star. And you can see that this is a multi-wavelength observation, and you can see a bowl-shaped structure. They are evaporated atmosphere of the companion star. So we indeed witness that pulsar can destroy the companion star. Millisecond pulsar can do this. Okay. But now the pulsar are spun up to millisecond level. As long as the magnetic field is high enough, or mass accretion rate is low enough, then the accreting material will touch the magnetospheric first and cannot reach the rotating radius. In this situation, those material will be ejected from the system due to the centrifugal barrier. So this is the so-called propeller region. And as long as the magnetic field and the mass accretion rate is fine-tuned to make the magnetospheric radius roughly the same to rotating radius, we can see sometimes spin up and spin down of the system. And we indeed find a lot, not a lot, a few these kind of systems. They sometimes spin up, sometimes spin down. And this is a long-term spin up plus a long-term spin down. So they are switching between spin up and propeller region, possibly. Although we still have many other explanations, just like switching between propeller disk and another accretion mechanism. Or they could have some retrograde disk. Sometimes for switching between prograde and retrograde disk, there are a lot of models still possible to explain. But in any case, a change in X-ray flux are needed for those models. And this is my work about a very special source, SMCX1. It is an X-ray pulsar with a spin period of roughly 0.7 seconds. And it is an existing binary system, but the most interesting thing is that it has a superorbital modulation. Superorbital means the period is longer than the orbital period. And this superorbital modulation can also be seen in optical band. And the period of the superorbital modulation is roughly 60 days, but sometimes it will evolve to 40 days, and then drop back to 60 days. And this so-called excursion event, we find that it could be recurrent with a time scale of 3,200 days. We still don't know why, but thanks to Maxi is an old sky monitoring program, but recently they released their raw data. And through those events, I used the old sky monitor to search for spin of this system. And I have to have a very precise orbital ephemeris and perform three-dimensional search, so I use GPU computing. And what I want to do is, because previously, in RST era, some astronomers claim that this spin period evolution may have connection to the superorbital modulation. But in my recent study, I find that no, they have no positive correlation. But those change in superorbital modulation frequency here, the change here, may have some connection to the change in torque, but not necessary to be positive or negative. So this implies that the disk, because the superorbital modulation is believed to be caused by the precession of a warp disk. And the warp inclination could be changed when the mass accretion rate or some configuration change. And the change in warp inclination angle will change the accretion torque. So it will change the spin up rate, but not necessarily to be positive or negative. That's previous talk is for disk-fed system. But for wind-fed system, the situation will be totally different. Because if it is so-called directed wind, there are no disks formed around the compact object. And in this situation, the accretion torques are quite random. So the entire evolution would be similar to a random walk instead of a scalar spin up or spin down. So this is just similar to a Brownian noise. But for two very spatial wind-fed systems, we find that, for example, in this system, the spin-up torque are always larger than spin-down torque. And the spin-up torque have a linear correlation here, correlate to its count rate. And this is another source. This is a very, neutron star with a very long spin period, roughly 3 hours. And we can see that this is spin period evolution. Sometimes it is spin up, sometimes it acts like a spin down or random walk. And during the so-called spin down or random walk, epochs, the superorbital modulation, the amplitude of superorbital modulation decrease. So we explained that the superorbital modulation could be related to the formation of transient disk. If this system has disk, then we have a stronger superorbital modulation, and we have a circular spin-up trend. And for example, when the wind from the companion star is strong, then the disk may be disappeared, and so the spin period evolution will similar to window. This is our explanation. So, of course, we know that X-ray binary, the compact object in X-ray binaries, can be neutron star or black hole. And observationally, black hole X-ray binary system could be a little bit dimmer than those neutron star X-ray binary systems. And they are believed, most of them are soft X-ray transient. They have outburst. And this is a model for an outburst. When the quiescent state, the disk is far away from the black hole. And the mass still accreting from the companion star, so it will accumulate on the disk. So the disk build up, and at some critical point, it jumps to the so-called outburst state. It has some ionization here, and the disk is also very close to the black hole, and the accretion is through a very efficient disk accretion state. So the spectrum looks like a steam accretion disk plus a steam power law. And this is the so-called Q curve or turtle diagram of a soft X-ray transient. And you can see the X-ray binary go from the so-called low Hart state to high soft state, and may jump between the so-called steep power state and the disk dominant state, and then go back to quiescent. Sometimes they go to steep power. But the entire process are strongly Edinburgh limited. The Edinburgh limit means that radiation pressure and the gravitational force are balanced, and it is roughly 10 to 38 erg per second if it is one solar mass system. So, for galactic sources, most of them are well Edinburgh limited, means that their luminosity is lower than roughly 10 to 39 erg per second. But in 1980s, roughly, astronomers find some extreme sources in external galaxies. They are not the AGN, not the core of the galaxy. They have luminosity higher than this value, than the Edinburgh luminosity of 10 solar mass or even 20 solar mass black holes. So they are ultraluminous X-ray sources. They are extremely bright. And astronomers were very happy because they could be candidates for a missing link between stellar mass black hole and the supermassive black hole. We know that the stellar mass black hole have roughly 20 solar mass, and supermassive black hole are roughly 10 to the 6, 7, or even 10 to the 10th of the solar mass. But they could also be stellar mass black hole with very strong binding, like microquasar. But from timing and spectrum observation, these two are not a major population of ULXs. And through the population study, we know that most of them are stellar mass black hole with super Eddington accretion and a mild beam. Means the beaming can, we don't need a very strong, just like a microquasar. We can have a mild beaming, and accretion is from another direction, so the mass accretion rate can exceed the Eddington rate. And most of non-ULXs are persistent sources. They are very different from soft X-ray transient. So they should have a different magnitude. And this is a spectrum of ULXs. They can describe with two components. First is a thermal component, and plus a power law with high energy color. So this is phenomenologically. But we can also use a more physical model to describe the spectrum. Just like a disk plus a complement corona. And if we use a picture to say that we are just like this. In regular soft X-ray transient, we can also describe the spectrum use these two components. But in regular X-ray binaries, we can see the innermost accretion disk and a thin corona. But for ULXs, we always need a very a disk with a very large inner radius, plus an optically thick corona. So they have some difference between ULX spectrum and black hole X-ray binary spectrum. But this spectrum can also be explained by another model, so-called supercritical accretion model. That is a mild beaming plus a disk. Here, it's not necessary to be a thin disk. It could be a slim disk or thick accretion flow, and plus a low energy thermal emission from the wind. But unfortunately, the model is still under developing, so we cannot use this to fit the observational data to test whether this is true or not, unfortunately. But recently, we find some transient ULXs. That means in regular echo, we do not see them. But when they go to outburst, the luminosity is much higher than the ideal luminosity of a 10 solar mass or 20 solar mass black hole. This is an example. NGC 7793P9 is a transient ULX. And it has two outbursts in the past 10 years. The first outburst, the luminosity is well below the ideal limit. So it is a regular soft X-ray transient. But after 2014, it goes super Edington outburst. And then we indeed see the spectrum fall from the disk dominant state and the power low state to ultraluminous state to become from one component to two components. But unfortunately, we still don't catch up the beginning of the outburst. So we do not know how it evolves from here or from here. We have no idea. So we need more observation to observe some more transient ULXs to see how they evolve from quiescent to ultraluminous state and how they go back to quiescent. They maybe go through here and go to the regular outburst state of the soft-X-ray transient and then evolve to ultraluminous state. Or directly go to ultraluminous state and evolve back through here or here. We still have no idea. We need more sample to test the theory. And in 2014, there is a very important discovery. That is, we see some pulsation in ULXs. That means ULXs could be powered by pulsar. We know that pulsar are much, the mass of a pulsar is much smaller than a black hole, the mass of a black hole. The mass upper limit of a neutron star is 2 or 2 point something solar mass. And black hole can be 10 or 20 solar masses. So this is a big discovery because it means that the super Edington, the Edington rate, Edington ratio of this kind of system is much higher than those of ULXs if they are powered by black hole. So we now have 8 pulsation ULXs. So how to explain the observed luminosity. And we can see that the spectral classification and luminosity cannot be an unambiguous way to classify ULSs, because we know that some of them are pulsars. So the previous classification cannot be applied to all the ULSs anymore. And because we know the alien rate is very high, so how to power those neutron stars to such high luminosity is a big problem. And one of the explanations is that those neutron stars may have a very high magnetic field. Because as long as the magnetic field is very high, simply speaking, the cross-section will be decreased, so the luminosity can be much higher. But if the magnetic field is very high, you will be in the propeller region. But we don't see this in pulsating ULSs. But actually, we see one of them has this phenomenon when we go to the low state. But anyway, they have no propeller, so maybe their magnetic field is not in the form of dipolar, colloidal form. They could be in so-called toroidal or multipolar form. Then they don't need. They can have a high magnetic field, and they do not enter the so-called propeller region. And this is the concept of magnetars. Magnetars are believed to have strong multipolar or toroidal magnetic field. So maybe pulsating ULSs are accreting magnetars, or at least accreting high magnetic field pulsars. But there is another model, so-called supercritical accretion model. As long as the beaming angle is low enough, we can always generate high enough observed luminosity. And someone said, no, all the ULS, maybe they are powered by pulsar, but they don't need to be magnetars. So these two theories still competing, and maybe some pulsating ULS have both strong magnetic field and some supercritical accretion. But if there are if this is correct, we expect that we may see some fast spinning pulsating ULS in the future, and which is not available with current X-ray observatory. SM Newton and Chandra, their timing resolution is not good enough. So we hope that in the future, if we have X-ray telescopes with good spatial resolution and good timing resolution, we may find some fast spinning pulsating ULSs. Maybe. And this is the most interesting phenomenon of pulsating ULSs. Most of them, if they are persistent sources, they have superorbital modulation. So superorbital modulation could be an indicator to find pulsating ULSs. But different from SMCS1, although SMCS1 is a superregional source. But this kind of ULSs, their superorbital modulation could be formed powered by precession of disk, precession of wing, or intrinsic accretion rate variability, or they are just switching between the so-called propeller and the regular accretion rate. So still have a lot of things to need to be verified. And this is one interesting pulsating ULSs, and we put on ULS7. Recently, I dig out Chandra observation, and I find that these sources have periodic dips. This is the first dipping pulsating ULSs. And in enormous X-ray binaries, dips are believed to be the obscuring effect of a central X-ray emission by the bulge, which is a string disk interaction region. So if a system has a dip, then we believe that the inclination angle cannot be too low. It should be a high inclination system. So that means that this system may, the beaming cannot be too strong, and which means that the magnetic field should be high enough to to have a high luminosity. So after some calculation, I find this system have a lower limit, magnetic field lower limit roughly 10 to 13 gauss. And this is consistent with some theoretical prediction of these source. And another implication is that the superorbital modulation of this system is not an intrinsic variability. It should be some obscuring of some precision result. So let us revisit the URS spectrum. The current two-component model cannot be an ambiguous method to classify URSs. So how about if there is a pulsating URSs and they show similar behavior? How can we explain the spectral behavior? So now the power low pulsar beam and the thin disk can contribute to the hardest emission. So we can naively use the power low to fit it, but physically they can come from two different components. And for the soft X-ray component, it could be from the wind or the outer disk. And possibly they still have some counter-night corona, sorry. So there are a lot of different components, but spectrally we can only see two components. That could be because simply because the spectral resolution is not good enough. So if we have good X-ray spectrum, we may resolve those different components in the future. So we know that URSs are accreting stellar mass black holes, or even most of them may be from pulsars. But there still have some URSs that are intermediate mass black hole candidates, but they are not, the number of them are not large enough to fill in the gap here. And as far as I know, the Ken is working on a first generation of star. They could form some 10 to a fifth order solar mass black hole here, but there's still a large gap here. And thanks for the gravitational wave observation, now we push the upper limit of a stellar mass black hole from 20 solar mass to roughly 160 solar masses. And I believe that in the future, we can push this upper limit to a much higher value. It is possible to fill in the gap. So the gravitational wave indeed opened a new window for astronomy. And we even see some neutron star merger, and I believe that all of you know that very well, so I will not describe it. But after, beyond the coalescence, how many other objects in the universe can emit gravitational wave? It is a big question in the upcoming 10 or 20 years. So current theoretical model suggests that maybe more than these three, but I just talk about these three. The first one is a continuous gravitational wave. If a neutron star is not symmetry, when it is rotating, it will emit continuous gravitational wave. When and the frequency is equal to the spin of a neutron star. Or two binaries. A binary system can also emit gravitational wave. Or when there is a thick gravitational flow, and the flow is not symmetry, have bulk motion. And those kind of motion can have so-called low result critical instability and emit gravitational wave. And they could have some connection to quasi-periodic oscillation in electromagnetic wave band. But the theoretical modeling is still ongoing. And another possible origin, now Han Guoquan in Tsinghua University is working on is a supernova. We know that in electromagnetic wave band, we see supernova is the final stage of the supernova explosion. But in the early stage, we must see the core of a high mass star. And only gravitational wave and the neutrino observation can do this. And when a proto-neutron star forms, and there are some accretion shock around it, and they have some bulk motion, and they could emit gravitational wave. And Han Guoquan is working on this, and I'm working on, I forgot to mention that. To detect them, of course, we need some good modeling and next generation of gravitational wave detectors. And we also need advanced time frequency analysis method. And this is why I'm working on. And I use a Hilbert-Hom transform, and I optimize it to detect gravitational wave. This is a refined algorithm, and this is a gravitational waveform generated by Han Guoquan, and I use it to see the time frequency map of the gravitational wave. And we hope that in the future we can indeed see those features from real data. And recently I also joined the NinjaSat project. It is a CubeSat project. CubeSat is very popular recently, and it is a CubeSat project led by RICAN, and there are a lot of collaborations here. We want to develop a 6-unit CubeSat, 10 centimeter times 20 times 30 centimeter, very small CubeSat, with 2 X-ray detectors. And the aim of this project is to monitor some bright X-ray pulsars and quasi-periodic oscillations, because they are candidates for continuous gravitational wave emitters. For example, we know that breakout frequency of a neutron star is 1 kilohertz. But the currently known neutron star has a much slower upper limit. So, what prevents neutron star from reaching this limit? It could be the interaction between the accretion disk and magnetic field, as I said before. And another possibility is that they are losing angular momentum through gravitational wave emission. And if this is true, then the gravitational wave radiation trend is like this way. So the great iridescent pulsar and kilohertz quasi-periodic oscillators could be the strongest continuous gravitational wave sources. And they are some of them are very bright, and we want to use a small satellite to monitor the spin period evolution of those systems. And in the future, we want to fold the gravitational wave data according to the ephemeris to get the continuous gravitational waveform. And there are some other scientific objectives of this CubeSat, or QPO as I said before, and we can monitor some pulsars to see some glitches. Glitches are a neutron star and have some deformation, or have some recombination of superfluid layer and the crust. And they could form some transient gravitational waveform. And we can use it to monitor orbital modulation across binaries and search for quasi-periodic in AGNs, because they could have some connection to Pavlovian Bringle instability and have some gravitational wave counterpart. So this is a QPO in X-ray binaries and AGNs. And we see a lot of quasi-periodic oscillation in X-ray binary systems, and some AGNs have quasi-periodic oscillations. But they are all narrow line sigma 1 galaxies. But this could be a biased result, because narrow line sigma 1 galaxies are believed to have a much lower black hole mass compared to other AGNs. So the quasi-periodic oscillation if they have a linear correlation to the mass, then the time scale of QPO in this kind of object is roughly a few hours. So we can use our current X-ray detector to observe this kind of quasi-periodic oscillation. But for those with higher masses, the time scale of a quasi-periodic oscillation is roughly a few days, a few weeks, or even a few months. The ideal instrument to detect those QPOs are O-sky monitor. But the current O-sky monitor program have not enough sensitivity to search for those QPOs. So this makes some room for CubeSat. We can use our NinjaSat or other CubeSat campaign to monitor some bright regions and to search for quasi-periodic oscillations. Okay. So I will leave my summary here, and if you have any question, please raise your hand.
Thank you very much. Any questions on Qingming's talk? Yijia?
I actually have two questions. So one is, what's the major difference between electrons in stellar black hole size and supermassive black hole size? Like you mentioned, the spectra the model for creating a spectra haven't developed yet for the pop-up model, right? In the middle.
No, I mean the spectral model for supercritical accretion is not well developed yet.
But so I work on the supermassive black hole area, and there's a model for that. And I don't know what's the reason behind for the stellar massive black hole doesn't have the model for that. So
Do you mean that we already have the model for supercritical accretion in supermassive black holes?
Yes.
We have theoretical model, but we still cannot directly apply it to data. There still have a gap between theoretical model and the data.
And
we have to use the model to fit the data.
So what's the gap?
I still have no idea. But maybe very good question. I still have no idea. But maybe in the near future they can compile a model to let observational astronomers to use the model to fit the data. In the near future, I believe.
And the second question is for the QPO you mentioned. I'm not sure about how common is a pulsar around the stellar mass black hole, but QPO is probably pretty rare compared to most of the AGN. And is there a reason why QPO is so rare compared to pulsar?
Pulsar.
Like I don't know, magnetic field. Can you explain the pulsar pretty well?
Yeah, the pulsation is from the spin of the neutron star.
Yes.
And they are coherent signal because they are just the spin of neutron star. But QPO is a phenomenon in the inner accretion disk. So they are from very different origin. So not necessary to all the sources may not have QPO, maybe. But there are some, as far as I know, some white dwarfs are found to have QPOs, and some magnetars during their burst, they can have some QPOs. But the origin is still unknown, because we know that magnetars have no accretion disk, but they can still have QPOs. Then those QPOs made from the seismology of the neutron star or something else. I have no idea. But the QPO I mentioned here are from the innermost accretion disk. And we know that the accretion disk size is proportional to the mass of the compact object. So the QPO frequency should have some linear correlation between frequency and the mass of the black hole. Yeah.
Good. Any other questions? Ms. Ken?
So I'm interested in your CubeSat project. So what's the principle that it would detect the continuous gravitational waves in X-ray? I mean, I don't know. Could you explain that, your CubeSat project?
We want to monitor the spin period evolution of low gravitational wave, candidate gravitational wave emitters. Because the continuous gravitational wave will be equal to, the frequency will be equal to the spin of a neutron star. So we need to build up a very long-term ephemeris and use these ephemeris to fold the gravitational wave data to see if we can see the profile.
So you want to see a pulsation, the spin period changing in X-ray, is that correct?
Yes. If there is pulsar, we can derive a very precise spin period evolution.
Then,
But for QPO, it is much
what's
harder.
the lifetime you expect for this CubeSat to?
Good question. The Ninja says, I believe that it is a prototype. So the lifetime is only 1 or 2 years. But it can provide a hint for future campaign of CubeSat.
Good. Any other final questions? No? No. So if not, let's thank Qingming again.